I win. Okay, thanks for your indulgence. I got it. We win. Okay, so let's go ahead and do a few slides in Chapter 1. Definitely will not go through Chapter 1. But, so look to see, there'll be some words missing in your PowerPoint handouts. So kind of see where the words are missing. So who in here, have y'all heard of the Hubble Space Telescope? Yes. Okay, so this image was taken by that cool telescope. The Hubble Space Telescope orbits the Earth. It's one of many telescopes that do that. And so actually the lights here are not stars, they're galaxies. Hubble Space Telescope. So speaking of that, one of the things in this class we're going to try to kind of get a handle on is kind of spatially how things are kind of set up in our universe. So the Earth orbits, what? The Earth orbits the sun. Right, exactly. Along with the other 7 planets in our solar system. Pluto is not a planet, right? So that's, and the sun is a star, okay? So actually, we are members of what galaxy? Starts with letter M.
Milky Way.
Milky Way galaxy. Great candy bar. Exactly. And the Milky Way galaxy is like a lot of galaxies, a spiral galaxy, okay? And it's kind of, it is in a, kind of like a frisbee sort of thing. It's kind of flat, Milky Way galaxy. And actually, our galaxy is kind of hanging out with a bunch of other galaxies, okay, called the local group, okay? Have you ever heard of Andromeda Galaxy? Yeah, that's a member of our set called the local group. And it's like they ran out of words to call it, so our local group of galaxies are further kind of hanging out with other groups, and it's called the local supercluster of galaxies. You're like, really? Okay, so that's kind of generally how things are. So in astronomy, we can't really use meters or kilometers or miles because the distances between objects are, yeah, they're ridiculous, exactly. So 2 ways of saying how far something is in astronomy to kind of get under your belt. One is closer than the other. A unit of length related to our solar system actually is an astronomical unit, an AU, and that's the average distance between the Earth and the Sun. But here's the deal, and some of you already know this. If I were to draw, okay, this is the, I don't know if you guys can see this. Let me do it over here. This is the Sun. Okay, there's the sun. Okay, and here's the Earth's orbit around the sun. And actually, it's not a circle. It's kind of like a, can you kind of see an oval? It's kind of flattened. Okay, and so there are some times when the Earth, I'll put E for Earth, sometimes the Earth is closer than others. Okay, actually, we call this, and I think soon we're going to call this perihelion, and this is aphelion. So that's Earth. What's the planet out past Earth?
Mars.
Very good, Mars. So actually Mars has the same sort of oval shape. M for Mars. What are the planets inside of Earth's orbit? What's the closest planet to the sun? Mercury, very good. Mercury. And then after Mercury is Venus, very good. Yep. Yep. So it's got that sort of thing going on. My whole point of this, I guess, would be is that, let me see, here's Earth. Oh, wait a minute. Yeah, here's Earth. This average distance is 1 AU. That's the average distance. So it does vary a little bit. The other distance in astronomy is even farther than an astronomical unit, much farther than an astronomical unit. It's called a light year. And I know it's weird because year is a time, okay? But it's basically the time, or it's the distance that light will travel in 1 year. And here's how this works, okay? If I go over here and turn off this light, well, that's kind of nice. Okay, when I flip on the power to that light bulb, okay, it will heat up the filament and cute little packets of energy called photons will be created, and they'll go in all directions. And they will be traveling at this speed, 186,000 miles per second. That's what photons travel at, lighter type of photon, okay? So they're traveling that fast. But now when I turn it on, the distance between me and that light bulb is so short that it's like, you know, it just happens right away, okay, right? I know it seems like there's a delay, but that's more in the little toggle switch than anything. But the light turns on, I see the light right away. But if I were to, let's take the 186,000 miles per second. So for instance, if that light was 186,000 miles away, it would be delayed 1 second to get to me. Does that make sense? Okay. So what a light year is basically you do the math and you locate an object far away that when it emits a photon, it takes a year for that photon to get to you. That's a light year. 1 light year. And it's a lot of miles. Okay, so 1 light year. Here's the thing about it, is that, for instance, the closest star to us is 4 light years away, 4.4 light years away. Alpha Centauri, you might know, heard of it. So that star, 4.4 light years away, okay, so when it emits photons, it takes 4.4 years for that photon to get to us, that little energy, that little piece of information from that star. 4.4 years. There's that delay. It's 4.4 light years from us, okay, and that's the consequence of it. So it's a ways, light years. Okay, so Jupiter, which is the planet past Mars, right? So what do we have after Mars? What's after Jupiter? Saturn. What's after Saturn? One of the blue planets. The other one. Yep, Uranus, and then Neptune. And what's after Neptune? Pluto. Yes, yes, yes. We all love Pluto. And it actually got a heart on it. Because, yeah. Okay. So Jupiter is 5.2 astronomical units from the sun. Jupiter is. Makes sense. Now, in terms of using light year as a distance, the Andromeda galaxy, that I said is in our local group, that's another galaxy. Here's our galaxy, they're like frisbees. And maybe some of you guys have heard this, that we're actually doing this gravity dance. And so Andromeda and the Milky Way galaxy actually are going to collide. Okay, it's kind of exciting, scary. But if you watch the same documentary I did, you know that when they collide, basically what will happen is in our nighttime sky, we'll just kind of see more of the Andromeda galaxy will get larger as they come closer. There's so much space between the galaxies that the stars won't collide. I wonder if their centers will kind of merge and form something interesting. The centers of most galaxies is a supermassive black hole, and that actually is in the center of the Milky Way galaxy. It's the center of Andromeda galaxy. Anyway, how far is that galaxy from us? 2.5 million light years. So that's, yeah, I know. You're like, really? Is that really going to collide? I just thought about it, yeah. 2.5 million light years. So hopefully this semester you'll get a chance to see the Andromeda galaxy through a telescope or through binoculars even. Andromeda can be seen through binoculars. It's a little fuzzy thing, naked eye. So Andromeda, that light that you see, it left that galaxy 2.5 million years ago. Isn't that not cool? Just amazing. Oh, I should have put this up. Here's Andromeda. So here's the Andromeda galaxy. It's also a spiral galaxy. It actually has a couple of dwarf, smaller galaxies that are much closer than the Milky Way. And actually, it's called cannibalism. So Andromeda is just going to gobble up the little ones. So I said you can see it naked eye. Actually, there it is kind of located between, there's a constellation called Pegasus, a constellation called Andromeda, so. You guys have the slide? No. I decided to kind of do just a little bit of talking about scientific notation. Anybody here who's familiar with scientific notation? Okay. Zach, sorry. The only reason, and we aren't going to do any like math in this, you don't need a calculator, but I just want you, if you're not familiar with it, to have a sense for what scientific notation means. Okay. So scientific notation is great for packing up big and little numbers. And scientific notation will always have what we call a coefficient for the decimal part. Coefficient. And it will have times 10 raised to a power. And this is the exponent part. Okay. So basically, if it's a big or a small number, what you do is you find where the decimal is and you move the decimal to the left or the right, whichever way you need to get like a number between 1 and 10. And then that number is going to be your coefficient. And then you take it times 10 raised to a power, and this power is the number of places you moved decimal. That's it. One more catch is if it's a small number, then you need to put a negative if it's a small number. So I just have some examples for us to kind of spot check. Because like in astronomy, sometimes we have really big numbers that are packed up using scientific notation. I kind of want us to have a sense for that. And small numbers, but more than likely big numbers. So let's, just for kicks, this one right here. So where is the decimal there, you think? Kind of at the end? Yep. I read what you were, yeah. It's at the end there. All right, so let's move it over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I get 11. 11 places you need to move it over. And the coefficient's going to be 5.9145. 5.9145 times 10 raised to what power? 11. Okay, so the bigger, as this number gets bigger, then it gets bigger by a factor of 10, right? That's kind of how that works. So let's pick on small number wise. Let's do this first one up here. So of course the decimal's right here. If I move it 1, 2, 3, 4, 5, 6, 7, 8, looks like 9 places to get between the 4 and the 7. So my decimal number will be 4.721 times 10. I moved it 9 places, so I'll put a 9 up there. But since it's a small number, yep, it's got to be a negative 9. So that's kind of how that goes. So we'll just kind of take those couples as an example. So anytime you see something in scientific notation with a negative exponent, negative power of 10, that means it's small. The bigger that negative exponent, the smaller it is. So that's kind of what I wanted you to get out of that. So time as a distance. You don't have this slide either, but this is just kind of, just bear with me. You'll do fine here. Let's say we use time as a distance all the time. Like, for instance, let's say you have a car that goes 60 miles per hour. 60 miles per hour. So that's like what? 1 mile a minute sort of thing. Okay. And let's say somebody says that event is 30 minutes away. Okay, 30 minutes away, well, it's 1 mile a minute, so it's really 30 miles away, right? So you have used time as a distance. Okay, and that's kind of what we do with a light year. So you do have this one. So back to the fact that light takes a certain amount of time to travel from point A to point B. It's really fast, but the farther away you are, it becomes significant with regard to how long it takes light to get to you. Okay? Here are some objects that emit light. The moon glows only because the sun shines on it. Okay, the moon doesn't have any internal source. It just reflects light from the sun. But based upon how close the moon is to the earth, it takes light 1 second to get here. From the sun's further than the moon, so it takes light from the sun 8 minutes to get here. So if you've watched some of these documentaries, it's like there'll be a delay. Like if the sun were to just vanish, we wouldn't know it for 8 minutes. Sirius, it's not the closest star, but Sirius is called the dog star, and it's in the constellation Big Dog, Canis Major, I think Canis Major. But it's it takes light 8 years to get here. So can you see where for Sirius, we would say that it is located 8 light years away. Its distance is 8 light years. 8 LY for light years. So here finally is a little bit, we can put to use the little exercise we did with scientific notation. So 8 light years to Sirius, doing the math in terms of kilometers, it's 7.6 times 10 to the 13th kilometers. So to unpack that, you take that decimal and move it over 13 places and add zeros. That's a lot of kilometers. Okay? Andromeda Galaxy, 2.5 million light years away, 2.4 times 10 to the 19th kilometers. So I mentioned, like, when we do get photons from Andromeda, they have been traveling for 2.5 million years. And like when they enter the telescope to enter your eye, I mean, they're gone, they're spent. That energy basically was, your mind used it to make sense of what you were looking at. So, I mean, it travels all that way just so we can see it. I just think that is so cool. So here's the deal, Andromeda, 2.5 million light years away. When we finally see it, does this make sense that in our shared space and time, it has aged 2.5 million years? You know what I'm saying? There's that delay. So we see it as it was 2.5 million years ago, and it has aged an extra 2.5 million years. Does that make sense? You can kind of look at it both ways. It's possible that, we're going to talk about how stars live their lives and some go out explosively and all that. You know, it's possible that some of those stars have lived their lives and died, but we just don't know it yet because we have to wait for the photons to get to us so we understand that. So here's the deal. And we'll be talking more about this in Unit 4 when we talk about the universe unfolding. I can't remember I don't think I told you this yet on Wednesday. I get my night and my daytime class mixed up. But, what was I going to say? That this universe had a beginning. Now, of course, we call that the Big Bang, right? Recently in the news, astrophysicists, physicists are kind of mulling over what really happened in the very first, like, fraction of a second of our universe being an entity. But really we can understand the laws of physics and go back into time pretty much close to that first beginning. But here's the deal. So when the Big Bang, right, it basically created maybe 3 things. Okay, it created the space. Basically, have you ever seen The Matrix? I kind of think of, like, I don't know, but the Matrix that we all walk around on. Okay, the universe, when it unfolded, created space, it created time, and it created matter. Okay, all of that stuff. Okay, and I keep going like this because one of the things, actually, we're going to hit probably on Monday, is that our universe is expanding. okay? It expanded initially, and it's still expanding. Not only that, but its expansion is going faster and faster and faster. Its expansion is what we say accelerating. So if you've ever heard of the big tear, the big rip, okay, that's kind of like, you know. And when things expand, they cool down. And so things can only cool to a certain point, and then, you know, so anyway, that's kind of what we got going on. So back to this. All right. So this Big Bang happened, the math and the science tells us about 14-ish, 13.6 billion years ago. 13.6-ish billion years ago. So picture this, okay, picture the, okay, and then like we eventually get born, our galaxy and our star and our planets eventually get born, right? Okay, so remember that 13.6 billion years ago. Here's the deal. Can you see where we cannot see an object that is 15 billion light years away? If we see an object that is 15 billion, say it's a galaxy, 15 billion light years away, that means that that galaxy has been emitting light, and it finally reached us, has been emitting light for 15 billion years. Okay, that's longer than our universe has been in existence. We bump up against what's called the cosmological horizon. What I just described is the limit to our observable universe. And there's something called Olber's paradox that I'm going to hit, I think in Chapter 2, your textbook talks about it. And what it says is, if the universe has always been, if stars have always been doing their thing, what they're doing now, they did 100 billion years ago, plus infinity years ago. If that's the case, then basically the light would eventually get to us, okay? And what Olber's paradox says is we should look out, and our at nighttime, it wouldn't be dark. Basically, at nighttime, when we kind of turn away from the sun, our star, we basically would see another just faint glow of other stars that have been living for the last 100 billion years plus, okay? Olber's paradox, and we don't see that. There actually is an edge to our universe, which that brings you to the whole multi-universe thing and all that, which I'm totally intrigued by, you know. So on here, here we see actually, this is a cute little observatory. Hiding in there is a telescope, okay? And this is, the telescope brings light to, concentrates it and spits it out an eyepiece so we can see it. And so we're looking at a couple of galaxies. One of the things about galaxies is we know the further away the galaxy, it's going to be older. Does that make sense? It's going to be older light. Like, for instance, this is 12 billion light years away. Okay, so we're seeing it as it was 12 billion years ago. Okay? And the cosmological horizon I spoke about is drawn on here too. I will say, and this is kind of amazing too. What they see back here at about the beginning of our universe is a hiss, a faint hiss. It's in the low energies. It's in the microwave energies. It's called cosmic microwave background. So they actually do see kind of the glow from original Big Bang. So that's how that works. Any questions? Just think that's so cool. All right. So Andromeda Galaxy is M31. Okay. If you go out to the observatory, or if you're just around people who are enjoying looking at celestial objects, looking at stuff in the nighttime sky, sometimes they'll refer to their M catalog number. So Andromeda is Messier object number 31. And just a little bit about the Messier objects. There are 110 Messier objects. This is a poster of the 110 Messier objects. And they came about in the late 1700s by a dude who was actually looking for comets. Okay? And one of the things about comets, we'll talk about them later, is if you're like me, I used to think, well, comets are kind of like meteors. They go, Okay, they kind of are, but they're so far away that comets, what they do is, we see the background stars, you see, the Big Dipper and Andromeda, and what you'll do is you'll see the comet, one night will be here, and the next night it will be here, and the next night it will be here. That's how comets move, okay? They move, what we say, against the background stars, okay? The thing about comets, quite frankly, is the reason they're moving is they're going to come orbit the sun, and they're going to go back out. And as they get closer to the sun, they kind of vaporize, and that's why we see it, and they'll go back out, okay? So comets move. He was looking for comets, and so he said, dude, so he assigned his, underlings to find these fuzzy things that weren't comets and say, get him out of the way, because I'm looking for comets. Okay, so these were his throwaways. So they're fuzzy things that oftentimes you can see through binoculars. And they kind of come in categories. You probably recognize, kind of see the spiral structure. These are spiral galaxies. Okay. The other thing that Messier found were, I love globular clusters. Okay, here's a globular cluster. A globular cluster is a cluster of stars. It's like if you take an ice cream scoop, and instead of scooping ice cream, you scoop stars, and throw them up in the sky. That's like what you get with a globular cluster of stars. The other thing that Messier found are open clusters. So there's globular clusters and open clusters. Anybody in here, and we'll be seeing some pictures of it, familiar with the Seven Sisters or the Pleiades? It's the same. It's like a cute little open cluster of stars that were born about the same time. So they're not a globular cluster, but they're an open cluster. So Messier cataloged those. The other thing is, do you see the color ones? Okay, like this one, okay, this one, this one. Those are all what we call nebula. And I have a slide later on defining what nebula is, but just think of nebula is, most of outer space is a vacuum, okay? Most of outer space is a vacuum. You might run into a star, and then most stars have planets. Maybe we already mentioned that. But if you're in outer space and you run into kind of like a fog or an extra place where there are atoms, maybe molecules, dust particles, that's a nebula. And actually, stars can be born in those nebula. And those nebula were created by stars, actually, in one form or another. Those are nebula. Well, I think this is a good place to stop. Don't you? I think so. So we'll start here on Monday. So nothing due. We definitely will get through Chapter 1 on Monday and begin Chapter 2. So don't forget to pick up your lecture slide notes.